This is the landing page of CemGEMS. And also from this page, you should have registered with this form and then receive an email with confirmation code, because otherwise we cannot really keep your work separate of everybody else's work. We just log in, which should be very easy. So with your username and password. So after logging in, if you haven't done anything yet with CemGEMS, you should see this screen here. Basically, what you can choose is new recipe. You can choose cement type. You can choose data type. I will later on show you what this means. What does this mean? And you can type in any name here. By default, it's just my recipe. And the same you can do with process. You can choose the process type, in this case, hydration MPK, but you always see like this drop-down lists. Here our cement types, process types, and then process lead, which means against what variable the process will be simulated. And then you also can give the process a name. When you are here at this screen, it's just enough to click on this button, simulate process, and wait about 10, 15, 20 seconds, depending on the load, because the calculations are done on server. So after this time, you should see this screen. Let me start with this plot first. So I will scroll a little bit the browser. So the results of process simulations are usually shown in such plots. And in this case, you see the plot for Portland cement hydration using modified Parrot and Kellogg model that Barbara teaches also on her GEMS courses. And here you can follow residual clinker phases as function of logarithmic time in hours. For instance, here I'm showing ferrite and B-light and A-light, C3S. And the rest of phases are hydrated phases that are forming during this hydration process. Hydrogarnet, CSH, Portlandite, AFT, ettringite, monocarbonate, calcite, because it was like calcite containing Portland cement. And then some minor stuff because we allow up to 19 chemical elements, so that you could use real analysis of clinker phases or cement or supplementary materials as they are. So, and then aqueous solution. What you also see here that we plot volume, so you see this chemical shrinking, how it develops with time. And then you can switch to different ordinates and different chart types. For example, I can only show here volumes of solids without water, just a little bit better to see masses of all phases, including water. So you see this process occurs at constant mass. And then also masses of solids only, total dissolved aqueous concentrations of elements. You can do exactly the same as I'm doing in parallel. And then aqueous pH, PE, EH, ionic strength, how it changes, this time is not interesting. And then reaction extents of clinker constituents controlled by this hydration model. So you see 5 and you see their curves against log time. And then also you can see heat rates. This is our latest new experimental part. So this is isothermal heat production or generation in milliwatt per gram. And this is adiabatic temperature rise rate in degrees per hour. So you can see this, we indeed get about 4 at maximum. And then what else we can finally plot is cumulative heat effects. In this case, this is cumulative isothermal heat. And this is adiabatic temperature rise. So you see we reach temperatures of about 70 or so centigrade. What you see on the plot, you also can see here in the data table when you click in this corner on triangle. And then you see numbers which are plotted. And you can also save any such table into CSV file by clicking on this button and then replot whatever you like. Okay, above we see the recipe from which we started. And here we see like initial state inputs, volumes of all these clinker constituents at the beginning, and also water, how much it was at the beginning. And then here you see final state, which means partial equilibrium, some residual clinker phases, and then hydrated phases which formed. You can hover mouse and it shows kind of tooltips, what it is and how much and so on. So that's basically like a graphical presentation of initial recipe in its initial and final equilibrated states. And the process generates 100 such recipes by systematically changing something in them. Well, let me show you first the input. So if you go to input recipes section and click here on this triangle, you will dive into the recipe, how it is organized. So basically here is the total recipe. You can dive in. You can see it consists of 4 materials: cement, SCM, water, and salts. And then you can dive into these materials. And for instance, in cement, you see these constituents or phases of clinker. And you see we can give amounts in various scales of all them, and we can give reaction extents. So which tells what fraction of this will actually react, equilibrate when I will equilibrate the recipe. And it's basically what we control in this modified Perrot and Killoch model or any other hydration model. Then we can dive in any of those constituents and see that its composition is set by this chemical formula and mass percentages, but also could be other units. So we basically provide quite a lot of information in these templates, out of which we create our recipes. And then you can modify anything which is on the white background here. So you cannot modify what is not on white background because it is calculated. But all stuff on white background you can modify. You can also change kind of global things like water binder ratio, temperature, pressure. For people who want to see more, you also have this expert view, which you can switch in the upper right corner. Okay. It just shows more columns in the tree-like tables. But otherwise, it still shows the same information which is contained in the process document. And then you can look at results and see in results, expanding them in exactly the same way. You can see equilibrated part and residual part. So I start first with residual part because it shows what did not react in our calculation of this recipe. And you see these are all residual quantities of clinker constituents that did not yet react because it was not allowed by their reaction extents, which we normally have in templates corresponding to 28 days of hydration time. And we assume that water and salts always react completely, so they do not show up in residual. Now we go into equilibrated part, and here we see what we normally also see in GEMS output, sorry. So we see the phases present in equilibrium state, all these names here in the list and their amounts in moles. We can dive into any phase and see its speciation, like here aqueous speciation or CSH, 6 end members with respective concentrations. It's all also recalculated into masses. For instance, on such plot like masses, we see all masses both of residual clinker minerals and of hydrated phases in every point of the process. And you see, of course, here you cannot edit anything because it's all calculated. So this is just the first look. What I wanted to show before we move on is also this entry, which is called phase analysis, because this is probably the only part where we can control thermodynamic system in this web application. All the rest is hidden. So all thermodynamic data is hidden, what you have access in GEM selector, because we want to keep it simple. So basically what this list of phase aliases lets us do is to assign or write aliases of names of the phases if you don't like those names that are given in GEMS, because these are names from GEMS. As you can see, also the same as in CemData database. But if I want to have them like longer or nicer or better self-explanatory, I can write here this phase aliases, and then I will see them in my lists or in plots. But even more important thing here is this column called restricted. So, because here these ticks, the blue ticks, they show what phases are not allowed to appear in equilibrated state, even though they might want to appear. And this is really what controls the shape of our chemical system. So we provide a template for this phase aliases list with some restrictions set based on our experience. So mainly Barbara's and Frank experience. But the good thing is that the user can always change this. Selection of restricted phases, allow some of them or restrict some other phases, what's going on. So just before we move to the next part of the training, let's exercise how do we live GEMS and how we get back to our work. There are basically two ways of living this web application: without logging out and with logging out. You come to a different machine, different browser, log in again, and then it will take all your work from central database saved there when you logged out and resume again exactly from the same place. And also one good thing when you log in is that all templates get automatically refreshed from central remote database, because we often fix templates for recipes, for processes. And in this way, when you log out and log in, you also get the latest version of templates. Okay, so this is more or less our first part of 3 finished.